Good morning, ladies and gentlemen. It's a pleasure for us, for Engine Software, hosting our partner ESRD, in particular its CEO, Mr. Riccardo Actis, for this series of webinars dedicated to this simulation app. We do believe in this very interesting technology as a part of the future of simulation governance and simulation democratization. Today, we open this series of webinar with webinar 1, which will talk about what are smart engineering simulation apps. The second will be held in the middle of July and will be about functional and technical requirements for a sim app. The third, on select, create, test, and deploy sim app, will be done at the end of July. And with the fourth, in September, we will close this series with examples and reference case studies. Now let me give the floor to Mr. Riccardo Actis, CEO of ESRD St. Louis. Thank you.
Thank you very much, Luca, for the introduction. Welcome all to the webinar 1, in which we will be introducing the concept of emerging simulation apps. Just as a teaser, here is sim apps some examples of sim apps in a CAE-Handbook, a product that we will be discussing in more detail during webinar 2. The topic for today will try to address the reasons why simulation has historically been performed by specialists. We are going to review why legacy FEA methods struggle with standardization and automation of simulation processes. And also, we are going to address in particular what are simulation apps, sim apps for short, why are they important, what are the benefits, and what are the challenges in creating and using them. But first, I would like to give you a few words about ESRD. Engineering Software Research and Development was founded by Drs. Barna Sabo and Ivo Babushka in 1989, and we have headquarters in St. Louis, Missouri, United States of America. We focus exclusively on computer-aided engineering and in reliability through simulation governance, and that is verification through the estimation and control of the error of approximation, validation through the estimation and control of the errors associated with the selection of mathematical models, and standardization through knowledge capture and simplicity. Our engineering software for numerical simulation is geared towards computational solid mechanics. We have been mainly working for applications in aerospace and defense, and we have been pioneering the development of smart engineering simulation apps over the last 10 years in this industry. So the first question we would like to explore is why not simulation for all? And one of the things that is worth noting is that the capabilities of finite analysis software for performing advanced simulation by expert analysts has increased rapidly over the last 20 years at a much faster pace than those available in tools for performing more routine work by non-experts such as design engineers. Unfortunately, despite several decades of continuing investment in simulation by the industry, design engineers still are not routinely performing simulation work. So why is that? Why simulation remains so complex and problematic that is mostly performed by specialists? The fundamental reason, which is often ignored, is that most simulation software do not produce a posteriori objective measure of the quality of the solution that can guide the non-expert user. Without experts always involved to compensate for this, the process and results of numerical simulations are risky. I always remember a conversation I had once with a technical fellow from Lockheed Martin Corporation, and regarding the utilization of numerical simulation techniques and experimental techniques. And he said, one of the problems that we always have is that everybody believes in the results of experiments except the person who did the experiment, and nobody believes in the results of the analysis except for the guy who did the analysis. And that perception is of lack of reliability in numerical simulation, one of the key reasons for it is the second bullet that you see there, that the objective measure of quality of the solution is not present. Existing simulation technology, as we said, struggle with automation simply because, not only because of the inherent complexity, but their inability to measure the solution quality. A different numerical technology developed at ESRD enables the creation and use of marine engineering simulation apps and digital handbooks that are more accurate, efficient, robust, and reliable, all with built-in quality assurance dashboard. So what do we mean by QA function? Let me show you an example of how it works. This will be considered this example shown here is a typical stress analysis in which an analyst may be requested to provide the maximum principal stress at a critical location in a component such as this will represent a section of a frame of an aircraft. Using a legacy fine element software, the analyst will obtain one solution utilizing the mesh that the analyst considers to be reasonable for the problem, report that value, and provide node solution verification. With the ESRD FEA technology, we will utilize the same mesh that the analyst designed, use hierarchy spaces, fine element spaces, to produce a sequence of solutions, and then as a result of that, we will have a measure of the quality, which is provided by the convergence information when the number of degrees of freedom is increased by using these hierarchy spaces. One of the things to note in this particular example is that the single solution produces a result which is 20% higher than the actual converged result. So the approach is with the same mesh, but a different FEA technology, we can have this additional and important component, which is an objective measure of the quality of the solution. So now let's focus on the principal topic of our presentation. What do we mean by simulation apps? Why they are important, benefits, and challenges. For simulation app, we mean FEA-based software tools for standardization and automation of recurring analysis tasks and process workflows. These simulation apps are developed by expert analysts for users who do not have the same expertise, who are not a specialist. They are designed to fit into a existing analysis process that capture the institutional knowledge and best practice of the organization and produce consistent results by testing and approved analysis procedures. Why are they important? One of the reasons that is recognized in the analysis community is that the proper application of numerical simulation procedures require expertise in computational engineering, which is not widely or readily available. The smart simulation apps allows to leverage this expertise for recurring analysis tasks and process workflow, similar to the expertise of a specialist in applied mechanics, which was made available through classical engineering handbooks. However, one of the important advantages is that of the final element-based simulation apps is that they can deploy models of much greater complexity than those available in engineering handbooks, because fewer simplifying assumptions and classical methods are possible, such as the methods that are available in books like this, shown on the left, and they can be adapted to industry, company, and product, and shown in the image. An example of simulation apps is this is one here, in which ESRD has developed a toolbox that deploys FEA's solutions for analysis of the structural details, two key ingredients, and easy-to-use interfaces, while giving analysts confidence in the computed data by providing convergence information of all the results. Just to give you a couple of brief comments about some of the tools, the single fastener analysis tool compute accurate joint stiffness for applications in global analysis, where this information is fed to the loss model. They can analyze single and double shear joints, and the configurations, what you see here on the left, the configuration is such that allows over 400 possible combinations of material properties, type of material, the presence of shimming, type of fasteners, washers, bushings, etc. And all this analysis is performed by doing a fully three-dimensional contact without the user participation in the creation of any of the meshes that are required. This tool is complemented by a multi-fastener analysis tool that allows the computation of load transfer for any arrangement of fastener layouts for splice joint, lap joints, and others, performing 2D contact analysis, which also provides the detailed stress distribution around the holes. And for example, the laminate cutout analysis tool was developed especially for the repair community of composite materials in aircraft. And whenever a damage is detected and it has to be removed, one of the requirements in the design of the repair is that the cutout has to have enough strength to support some limit load, and they use this tool for determining that before the repair is authorized to be performed. And CAE-Handbook is another tool that we will discuss in more detail in the next webinar. The benefits are clear, making difficult classes of simulation problems easier to analyze, more accurate, faster to solve by the specialists to support increasing complexity in products and demanding design cycles. They also creating a new, higher value role for the CAE specialist to define, author, and support CMAPs across the organization and industry, creating intellectual property for themselves as an employer. So there is a new role, more creative role, that will take place for the specialist analyst. Also, it makes routine classes of design problems solvable by designers and engineers, similar to what was possible or was done in the past with traditional handbook and design curves. And also will empower new engineers to be productive sooner, because they will have access to reliable technology that capture the institutional knowledge and best practices with the distribution of the simulation apps. Just a brief comment about who is talking about simulation apps currently. For reference, this is a research brief based on the latest conference by NAFEMS in 2016. This happened between June 7 and June 9 this year, this month. And there was a mini symposium devoted to democratization of simulation. And some of the presentations were from other providers of simulation app, like Comet Solutions, from end users that related their experience in the democratization process that they are incorporated into their institutions, like American Axle Manufacturing Company, and from software vendors such as MSC Software and ANSYS. And we have our own presentation in this mini symposium, and we will be addressing some of the topics covered there in the next webinar. So what are the challenges in the development and deployment of simulation apps? The first one is the definition and enforcement of modeling rules. It's important to ensure that modeling assumption, meshing rules, element selection, extraction of results are consistent with the principle and method of numerical simulation, always keeping in mind that the end user may not be a specialist. Other challenges are the expertise and time required to anticipate all variation and use cases. And the problem here, the most interesting problem here, is that this depends on the expert to create and manage, and if the proper technology is not used, also including the performance of the quality assurance. And finally, the return of investment from process automation could be problematic due to the overall complexity and time to create by expert before allowing non-expert to use, if the proper technology is not used for the deployment. One of the things that is important to remark is the fact that legacy fine element analysis software tools struggle with simulation apps. And what is the reason for that? Are several, and we are going to list just a few, but for example, geometric approximation with low order mapping is problematic, and in general that forces a lot of defeaturing of the models, which can be problematic if the goal of the computation is to determine large peak stresses. Meshes and elements many times require restrictions that only an expert can understand and are dangerous to use without the expert. And the solution of high-fidelity multi-scale problems are complicated. The solutions are not continuous but discrete, nodal-based, making it difficult to get accurate stresses in regions of high-stress concentrations. The idea of a multi-scale problem, high-fidelity multi-scale problem, is illustrated with this example. What you see here on the top right is an assembly of thin web components of an aircraft structure that are connected by fasteners. This particular example was an application that we developed for one of our customers, in which the main goal of this was to determine the effectiveness of this element here called the shear clip and transfer the shear between the back end and the front and the main spar of this assembly. What you can see, the different scales, the size of the furnace are very small in comparison with the dimensions of the component, and the goal is not only to get the load transfer, but then afterwards, what are the stress distribution in the critical components, because this is a fatigue critical part. For traditional final element softwares, handling this with 3D solids is extremely difficult, if not impossible. Other factors that why legacy FEA struggle with simulation apps is that they cannot tell how accurate the solution is for every set of input and results of interest. Need to ask the expert author of the sim app for whether the solution is good. And the problem with that is that an expert is needed to tell when the solution is right. Then the expert is also needed to tell when it is not. And a non-expert user is not qualified to make that determination. 3D solid modeling of large-scale geometry is also challenging, especially within domains, as we saw in the previous slide, the example in the previous slide. And a complicating factor for the legacy FEAs is the large element libraries and mixture of the compatible models. And many of you may be familiar with the use of shell solid, shell beam, etc., which compound the problem. Just to give you an idea, this is an example of an element library, and this is one small sample because typical element libraries are 200 or more elements. This is a small sample. But if you pick one element in particular here, a 20-node quadratic brick with reduced integration, the question is how to interpret what it means, reduced integration, and what is the problem. One of the things that was discovered back in the 1970s is that reduced integration was a way to answer the question why the structure seemed to be so stiff. It was found that reducing the number of quadrature points, the element became more compliant. So here's when there is an unrealistic expectation. The reason why the structure was too stiff is because the error of approximation caused by low-order elements. And the reduced integration was considered to be the solution because it was assuming that always the error produced by the low-order elements will be cancelled by the error of integration, which is really not is an unrealistic expectation. Additional problem with reduced integration elements is instability because they are prone to a phenomenon known as hourglassing, which are zero energy modes of the formation. Unfortunately, this type of element makes solution verification impossible. So, what is the answer to these challenges? This will be addressed in webinar 2, when we will examine the functional and technical requirements for the creation and deployment of simulation apps. These technical requirements of simple and standard, accurate and complete, fast and efficient, robust and reliable will be addressed in detail. And if those are met, then the simulation app can be considered to be smart. And this is what we will be addressing in detail during the next webinar session. I would like to point to you, for if you have interest in more information about this technical requirement, to visit www.esrd.com for a copy of the paper that you see indicated here, and for more information about this technology in preparation for the next webinar. And with that, I'd like to thank you for your attention, and just a brief reminder of what Albert Einstein once said: everything should be made as simple as possible, but not simpler. And that requires a lot of loving and tending care in preparing these implementations. Thank you very much.
Thank you very much, Ricardo, for this very interesting presentation, and thank you to all of you for your participation. The next appointment will be on July the 14th with our second webinar of the series. Ricardo will give us a view about functional and technical requirements for CMAPs. Goodbye.